So we're going to be covering hopefully 4 sections today. They're brief sections, so we'll try to move quickly through them all. Elementary numbers and number theory and methods of proof. Number 4, divisibility. When you were first introduced to the concept of division in elementary school, you were probably taught that 12 divided by 3 is 4, because if you separate 12 objects into groups of 3, you get 4 groups with nothing left over. You may also have been taught to describe this fact by saying that 12 is evenly divisible by 3, or 3 divides 12 evenly. The notion of divisibility is the central concept of one of the most beautiful subjects in advanced mathematics, and if you can call it beautiful, number theory, the study of properties of integers. If n and d are integers, definition here, n is divisible by d if and only if n equals d times some integer and d does not equal 0. Instead of n is divisible by d, we can also say that n is a multiple of d. D is a factor of n. D is a divisor of n, or d divides n. The notation here is read d divides n. Symbolically, if n and d are integers, that means that there exists an integer, say k, such that n equals d times k and d does not equal 0. The notation that d does not divide n is right here. Is 21 divisible by 3? Yeah. Does 5 divide 40? Yeah. 7 divide 42? Yeah. Is 32 a multiple of minus 16? I see mixed reactions. Yes, it is. Minus 2 is the other factor. Is the other factor of multiply minus 16 by minus 2. 6 a factor of 54? Yeah. Is 7 a factor of 7? Minus 7? Yeah. Yes to all the above. So, yeah, you just got to think about it sometimes in terms of negative numbers. If k is any non-zero integer, does k divide 0? Yes, because 0 equals k times 0. So it does divide 0. 2 useful properties of divisibility are: 1, that if one positive integer divides a second positive integer, then the first is less than or equal to the second. And 2, that the only divisors of 1 are 1 and minus 1. So, theorem 441. For all integers a and b, if a and b are positive and a divides b, then a is less than or equal to b. And theorem 442, the only divisors of 1 are 1 and negative 1. If a and b are integers, is 3a plus 3b divisible by 3? Is 3a plus 3b divisible by 3. Yes, because you can factor out the, use the distributive law to take out the 3 and leave a plus b behind. If k and m are integers, is 10km divisible by 5? Yes, because 10 is divisible by 5, and km are integers. K and m are integers. So the associative law applies. When the definition of divides is written formally using the existential quantifier, the result is this here. There exists an integer k such that n equals d times k, and d does not equal 0. Since the negation of an existential statement is universal, it follows that d does not divide n if and only if for all integers k, n does not equal d times k, or d equals 0. In other words, the quotient n divided by d is not an integer. So for all integers n and d, n divided by d is not an integer. In the case of d being 0, it's not a real number at all. But that still means it's not an integer. Does 4 divide 15? Nope. Because it's not an integer. An alternative way to define a prime number is to say that an integer n greater than 1 is prime if and only if its only positive integer divisors are 1 and itself. Proving properties of divisibility. Prove that for all integers a, b, and c, if a divides b and b divides c, then a divides c. Transitivity of divisibility. See if we can prove that. Since the statement to be proved is already written formally, you can immediately pick out the starting point and the conclusion. Suppose a and b and c are particular but arbitrarily chosen integers such that a divides b and b divides c. Show a divides c. Or in other words, the c equals a times some integer. Since a divides b, b equals a times r for some integer r. Since b divides c, c equals b times some integer s. So since the second statement expresses c in terms of b, the equation and the previous one in terms of a, you can substitute 441, this one, into 442. When you do that, you have c equals ar times s, and by the associative law, you can say c equals a times rs, and a times something is what c is. But the product rs is an integer because it is a product of two integers. So for all all integers a, b, and c, if a divides b and b divides c, then a divides c. And divisibility by a prime. Any integer n greater than 1 is divisible by a prime number. Counterexamples and divisibility. Is the following statement true or false? For all integers a and b, if a divides b and b divides a, then a equals b. You think that's true or not true? Not true? All right, we'll see here. The statement is false. Can you think of a counterexample? To discover the truth or falsity of a statement such as the one given above, start off much as you would if you were trying to prove it. So, suppose a and b are integers such that a divides b and b divides a. Must it follow that a equals b, or could it happen that a does not equal b for some a and b? Focus on the supposition. What does it mean? So we got b equals ha, and a equals kb for some integers h and k. Must it follow that a equals b, or can it be found, or can you find integers a and b that satisfy the equations for which a does not equal b? No. You can solve for b, since b divides a, extreme left and right sides, you can cancel b from the extreme left and right sides to obtain 1 equals hk, which h and k are divisors of 1, but by theorem 442, the only divisors of 1 are 1 and minus 1. Thus, h and k are both 1 or both minus 1. If h and k equal 1, then b equals a. But if h and k equal minus 1, then b equals minus a. So a does not equal b. This analysis suggests that you can find a counterexample by taking b equals minus a. For the formal answer, you can let a equal 2 and b equal minus 2, and show that the statement is false. Unique factorization of integers theorem. The most comprehensive statement about divisibility of integers is contained in the unique factorization of integers theorem. Because of its importance, the theorem is also called the fundamental theorem of arithmetic. The unique factorization of integers theorem says that any integer greater than 1 is either prime or can be written as a product of prime numbers in a way that is unique except for perhaps the order in which the primes are written. For example, 72 equals 2 times 2 times 2 times 3 times 3. Also, with the 2's and 3's in different order because of the associative property of, or the commutative property of multiplication. Any factor of 72 as a product of primes must contain exactly two threes and 3 2's. No other collection of prime numbers besides 3 2's and 2 3's multiplies out to 72. Unique factorization of integers theorem. Given any integer n greater than 1, there exists a positive integer k, distinct prime numbers p1, p2, p3, etc. to pk, and positive integers e1, e2, etc. to ek, such that n equals p1 to the e1 times p2 to the e2 times p3 to the e3, etc. to pk to the ek. And any other expression for n as a product of prime numbers is identical to this, except for perhaps the order in which the factors are written. Definition. The standard factored form is an expression of the form given here, where k is a positive integer, p1 through k are prime numbers, and e1 through ek are positive integers, and p1 is less than p2, which is less than others, which is less than pk. So you write them in the ascending order of prime factors. So write 3300 in standard factored form. Well, you would have 3 times 11 times 100, which is 3 times 11 times 10 times 10, which is 3 times 11 times, I should make these here so they're not confused with x's, 2 times 5 times 2 times 5. So those are all prime numbers, right? So that would be the prime factorization. But in standard form, put the 2's first. 2 squared times 3 times 5 squared times 11. Make sense? Ascending order from 2 to 3 to 5 to 11. And so we have they put the 1s on the 3 and the 11, but it's 2 squared plus or times 3 times 5 squared times 11. Suppose m is an integer such that 8 times 7 times 6 times 5 times 3 times 2 times n, or m, equals 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10. Does 17 divide m? Given those two quantities. Does 17 divide m? You're probably going through this the long way. There's a little shortcut. 17 is a prime factor. So it doesn't matter what all these numbers are. It doesn't matter what all these numbers are. 17 is a prime factor of this number, of which m is a part. So 17 must divide m because it is a prime factor of the overall number on both sides. Make sense? Yeah. So since 17 is one of the prime factors of the right-hand side of the equation, it is also a prime factor of the left-hand side by the unique factorization of integers theorem. But 17 does not equal any prime factor of 8, 7, 6, 5, 4, 3, or 2 because it is too large. Hence, 17 must occur as one of the prime factors of m. And so 17 divides m. All right, and that is it for that side deck. Elementary number theory and methods of proof. Direct proof and counterexample 5. Division into cases and the quotient remainder theorem. I believe we mentioned the quotient remainder theorem last session, but this is where we get into it. The quotient remainder theorem. Given any integer n and positive integer d, there exists unique integers q and r such that n equals dq plus r, and r is greater than or equal to 0 but less than d. If n is positive, the quotient remainder theorem can be illustrated on the number line as follows. You have d, 2d, 3d, etc. to qd, and the difference of r to get n. If n is negative, the picture changes. Since n equals dq plus r, where r is non-negative, d must be multiplied by a negative integer q to bring dq either exactly to n or to a point below n, in which case the positive integer r is added to bring dq plus r back up to n. So it shows here on the number line like that. For each of the following values of n and d, find integers q and r such that n equals dq plus r, and r is greater than or equal to 0 but less than d. N equals 54, d equals 4. Now, let's see here. Q equals 13. R equals 2. Sound about right? Sound right? Yeah. This would be minus 14 and 2. And this would be 1 and 16. R equals 16. Right? Sound about right? I'm just doing this stuff in my head, so I don't know. I'm not a human calculator. But let's see what they say. 4 and 13 plus 2. 4 times minus 14 plus 2. And 0 plus 54. Okay. I was thinking the other way around. Yeah. Div and mod functions. Given an integer n and a positive integer d, n div d is the integer quotient of when obtained when n is divided by d, and n mod d is the non-negative integer remainder obtained when n is divided by d. This is the modulus function that you have in C++. So how does it work, and what is it? Oh, and regular division of integers in C++. So symbolically, if n and d are integers and d is greater than 0, then n div d equals q and n mod d equals r, if and only if n equals dq plus r, where q and r are integers and r is greater than or equal to 0 and less than d. So it ties it to the quotient remainder theorem. So compute 32 div 9 and 32 mod 9 by hand or with a 4-function calculator. What is 32 div 9? What's 4 times 9? 36, which is greater than 32. So that can't be right. So it would be 3. And then 32 mod 9? What's 32 minus 27? 5. So yeah, get the division by hand. Gives you the two values. To compute n mod d, substitute n div d in place of q and n and n mod d in place of r in the equation n equals dq plus r. The result is n equals d times n div d plus n mod d. Solving for n mod d gives you n mod d equals n minus d times n div d. So when you use a 4-function calculator to divide 32 by 9, you obtain an expression like 3.555, yada, yada, yada. Discarding the fractional part gives you 32 div 9 equals 3. So substitute that in, give you 32 minus 9 times 3 equals 32 minus 27 equals 5 for the remainder, for mod 32 mod 9. Prove that if n is a positive integer and then n mod 10 is the digit in the ones place in the decimal representation of n. So yeah, that's true. Suppose m is an integer. If m mod 11 equals 6, then 4m mod, what is 4m plus, or mod 11? Proof of A. Suppose n is any positive integer. Decimal representation is given here. where the digits are integers from 0 to 9 inclusive. dk does not equal 0 unless n equals 0 and k equals 0. And d0 is the digit in the ones place. Factoring out 10 from all but the final term gives 10 times this quantity here, which is an integer, plus d0. So n mod 10 equals the digit in the ones place. So because n mod 11 equals 6, the remainder obtained when m is divided by 11 is 6. This means that there is some integer q so that m equals 11q plus 6. Thus 4m equals 44q plus 24. 44q plus 22 plus 2 is 11. 4q plus 2 plus 2. Since 4q plus 2 is an integer, and since 2 is less than 11, the remainder obtained when 4m is divided by 11 is 2. Therefore, 4m mod 11 equals 2. You can calculate the mod of a number without necessarily knowing what the number is. Representations of integers. We defined an even integer to have the form twice some integer. At that time, we could have defined an odd integer to be one that is not even. The fact that any integer is either even or odd is called the parity property. Prove that given any two consecutive integers, one is even and the other is odd. Two integers are called consecutive if and only if one is one more than the other. So if one integer is m, the next consecutive integer is m plus 1. To prove the given statement, you could divide the analysis into two cases. Case 1, where the smaller of the two integers is even, and case 2, where the smaller of the two integers is odd. Case 1, in this case, m is equal to 2k for some integer k. So m plus 1 equals 2k plus 1, which is odd by the definition of odd. Hence, in this case, one of m and n plus 1 is even and the other is odd. Case 2, in this case, the m is equal to 2k plus 1 for some integer k. So m plus 1 equals 2k plus 1, which is equal to 2k plus 2, which is equal to 2 times the quantity k plus 1. But k plus 1 is an integer because it is the sum of two integers. Therefore, m plus 1 equals twice some integer, and thus m plus 1 is even. Hence, in this case also, one of m and m plus 1 is even and the other is odd. It follows that regardless of which case actually occurs for the particular m and m plus 1 that are chosen, one of m and one of n plus 1 and n plus 1 is even and the other is odd, which is what was to be shown. So, any two consecutive integers have an opposite parity, the parity property. Method of proof by division into cases. Prove a statement of the form if A or B, A1 or A2 or AN, then C. Prove all the following. If A1, then C. then if A1 is A2, then C. If AN equals, then C. This process shows that C is true regardless of which case happens to be the reality. Show that any integer can be written in one of the four forms for some integer q. N equals 4q, n is equal to 4q plus 1, n is 4q plus 2, or n is equal to 4q plus 3. Well, given any integer n, apply the quotient remainder theorem to n with a divisor equal to 4. This implies there exists an integer quotient q and a remainder r such that n equals 4q plus r. And r is less than or equal to less than 4, but greater than or equal to 0. But the only non-negative remainders are less than 4, that are less than 4 are 0, 1, 2, and 3. Hence, n equals 4q or 4q plus 1 or 4q plus 2 or 4q plus 3 for some integer q. In other words, n mod 4 equals 0, 1, 2, or 3. Prove. The square of any odd integer has the form of 8m plus 1 for some integer m. If checking some examples convinces you that the statement may be true, begin to develop a good proof by asking, what am I starting from? And what do I need to show? To help answer these questions, introduce variables to rewrite the statement formally. They give a formal restatement here. From this point, you can immediately identify the starting point and what is to be shown. Thank you. Is that going to be the only one? Maybe. Suppose n is a particular but arbitrarily chosen odd integer. Show that there exists an integer m such that n squared equals 8m plus 1. It looks tough. Why should there be an integer m with a property that n squared equals 8m plus 1? That would say that n squared minus 1 divided by 8 is an integer, or that 8 divides n squared minus 1. Perhaps you can make use of the fact that n squared minus 1 equals n minus 1 times n plus 1. Does 8 divide n plus 1 times n plus n minus 1, so typo there, times n plus 1? If n is odd, or since n is odd, both n plus 1 and n minus 1 are even. That means that their product is divisible by 4. But that's not enough. You need to show that the product is divisible by 8. You could try another approach by arguing that since the n is odd, you can represent it as 2q plus 1 for some integer q. Then n squared equals 2q plus 1 squared, which is equal to 4q squared plus 4q plus 1, which is equal to 4 times q squared plus q plus 1. It is clear from this analysis that n squared can be written in the form of 4m plus 1, but it may not be clear that it can be written as 8m plus 1. Yet another possibility is to use the result of example 456. That example showed that any integer can be written in one of the 4 forms given here. 2 of these are odd. Thus, any odd integer can be written in the form of 4q plus 1 or 4q plus 3. You could try breaking it into cases based on these two different forms. The fact that it is true that the square of any odd integer has a form of 8m plus 1. Take note of this problem and lack of solution in the slides, as it may appear on the midterm. So prove that you can prepare a proof before midterm and bring it in as part of your notes. The square of any odd integer has the form 8m plus 1 for some integer m. So go write this down and be prepared for that on the midterm. All right, that's it for that slide deck. That was 5, we need to go 6. Number theory and methods of proof. Proof and counterexample, floor and ceiling. Imagine a real number sitting on a number line. The floor and ceiling of the number are the integers to the immediate left and to the immediate right of the number. Unless the number is an integer, in which case the floor and ceiling both equal the number itself. Many computer languages have built-in functions that compute floor and ceiling automatically. These functions are very convenient to use when writing certain kinds of computer programs. In addition, the concepts of floor and ceiling are important in analyzing the efficiency of many computer algorithms. So, definition. Given any real number x, the floor of x, denoted by the half bracket here, is defined as follows. That unique integer n such that n is less than or equal to x and n is less than n plus 1. Symbolically, if x is a real number and n is an integer, then the floor of x equals n if and only if n is less than or equal to x and x is less than n plus 1. Definition of a ceiling, which is denoted by the brackets going kind of above the x, is the unique integer n such that n minus 1 is less than x and x is less than or equal to n. Symbolically shown here. Basically, floor is rounding down, ceiling is rounding up. There you go. If it's not if x is not an integer. Compute floor of x and ceiling of x for each of the following values of x. 25 divided by 4. What's the floor and ceiling? 25 divided by 4. What's the floor? 6. And the ceiling? 7. Floor of 0.999. The floor of 0.999. It's not an integer, so what's the next integer lower? 0. And the ceiling would be 1. Now the floor of minus 2.01. No. -3. -3. It's the next integer lower. And the ceiling? -2. On some calculators, the floor is sometimes denoted by the int x, where it just truncates the fractional value. So there you go. There are 1,370 students at a college, and they're given the opportunity to take buses to an out-of-town event. Each bus holds a maximum of 40 passengers. For reasons of economy, the leader of the event will send only full buses. What's the maximum number of buses the event leader will send? What's 1,370 divided by 40? I'm sorry? 34? Did you divide it by 4 or did you? 40. Okay, so 34. Okay, so what's the floor value of that? 34. In the event that the leader is willing to send one partially filled bus, how many buses would it take to send all 1,370? 35. Yeah. Is the following statement true or false? For all real numbers x and y, the floor of x plus y equals the floor of x plus the floor of y. Is that true? No, it's not. Can you find a counterexample?
For example, if x was 2 and y was 7, that's like 2 plus 7.
Uh-huh.
The floor of 7 would not equal to the floor of x.
The floor of 2 and the floor of 2 plus 7 would be 9, right? The floor of 7 plus the floor of 2 would equal to 9, wouldn't it? What if you took the numbers 1/2 and 1/2?
It would not be that.
0 does not equal 1. So, yeah. So that would be a counterexample. To arrive at this counterexample, you could have reasoned as follows. Suppose x and y are real numbers. Must it necessarily be the case that the equation is true, or could x and y be such that x plus y floor is not equal to floor of x plus floor of y? Imagine values that the various quantities could take. For instance, if both x and y are positive, then floor of x and floor of y are integer parts of x and y, floor of x and y, respectively, just as 2 3/5 equals 2 plus 3/5. So x equals floor of x plus the fractional part of x. And same with y, where the term fractional part is understood here to mean the part of the number to the right of the decimal point when the number is written in decimal notation. Thus, if x and y are positive, x plus y equals floor of x plus floor of y, plus the sum of the fractional parts of x and y. But also, x plus y equals the floor of x plus y plus the fractional part of x plus y. These equations show that if there exists a number x and y such that the sum of the fractional parts of x and y is at least 1, then a counterexample can be found. With the counterexample being 1/2 and 1/2. One counterexample. Prove that for every real number x and for every integer m, x plus m equals x of the floor of x plus m. Now, m is a real number, or is a integer, so the floor of m, x plus m, can be how do they do this here? Okay, begin by supposing that x is a particular but arbitrarily chosen real number and m is a particular but arbitrarily chosen integer. Since this is an equation involving x and floor of x and the floor of x plus m, it is reasonable to give one of these quantities a name. Let n equal the floor of x. By definition of floor, n is an integer, and n is between, or x is between n and n plus 1. Double the inequality enables you to compute the value of m. This double inequality enables you to compute the value of x, if the floor of x plus m in terms of n, by adding m to all sides. And thus the left-hand side of the equation is shown to be n plus m. On the other hand, since n equals the floor of x, the right-hand side of the equation to be shown is the floor of x plus m equals n plus m. Thus, the floor of x plus m equals the floor of x plus m. This discussion is summarized as follows. For every real number x and every integer m, the floor of the quantity x plus m equals the floor of x plus m. For any integer n, the floor of n over 2 equals n over 2 if n is even, and n minus 1 over 2 if n is odd. Given any integer n and any positive integer d, the quotient remainder theorem guarantees the existence of unique integers q and r, such that n equals dq plus r, and r is less than or greater than or equal to 0 but less than d. The following theorem states that the floor notation can be used to describe q and r as follows. Q equals n over d floored, and r equals n minus d times n over d floored. So another way to express the quotient remainder theorem. Thus, if on a calculator or in a computer language, floor is built in but div and mod are not, div and mod can be defined as follows. For a non-negative integer n and a positive integer d, n div d equals the floor of n divided by d, and n mod d equals n minus d times the quantity n over d floored. Note that d divides n if and only if n mod d equals 0. In Floor notation, this means that n divides n if and only if n equals d times the floor of n times d. Different ways of expressing the same thing. Theorem 463. If n is any integer and d is a positive integer, if q equals the floor of the quantity n divided by d, and r equals n minus d times the quantity n over d floored, then n equals dq plus r, and r is greater than or equal to 0, and d is and r is less than d. Use the for notation to compute 3850 div 17 and 3850 mod 17. I'm not going to go through all that right now. By formula 461, n div d equals the floor of n divided by d, which in this case equals 226. N mod d equals n minus d times n mod d, n divided by d floored. So 3850 minus 17 times 226 equals 8. And that's it for that slide deck. 20 minutes to do one more. Let's see here. And that's 7. All right. Number theory and methods of proof. Indirect argument. Contradiction and contraposition. Up until now, we've been just talking about direct proofs. We'll be doing more indirect proofs now. Indirect proofs are more roundabout. One kind of indirect proof, argument by contradiction, is based on the fact that either a statement is true or it is false, but not both. So if you can show that the assumption that a given statement is not true leads logically to a contradiction, impossibility, or absurdity, then that assumption must be false. Hence, the given statement must be true. This method of proof is also known as reductio ad impossible or reductio ad absurdum, because it relies on reducing an assumption to an impossibility or an absurdity. Method of proof by contradiction. Suppose the statement to be proved is false. That is, suppose that the negation of the statement is true. Show that this supposition logically leads to a contradiction, and conclude that the statement to be proved is true. Use proof by contradiction to show that there is no greatest integer. Well, for this proof, the certain property is the property of being the greatest integer. So prove that there is no object with this property. Begin by supposing the negation, that there is an object with the property. Suppose not. Suppose there is a greatest integer, call it big N. This means that big N is greater than or equal to n for every integer little n. This supposition leads logically to a contradiction. And there is no, theorem 471 is there is no greatest integer. The fact that no integer is both even or odd can also be deduced from the uniqueness part of the quotient remainder theorem. There is no integer that is both even and odd. So, yeah, theorem 471-2. No integer can be both even and odd. Use proof by contradiction to show that the sum of any rational number and any irrational number is irrational. Begin by supposing the negation of what we are to prove. Be careful when you're writing this down. If you take the negation incorrectly, the entire rest of the proof will be flawed. In this example, the statement to be proved can be written formally as, for all real numbers R and S, if R is rational and S is irrational, then R plus S is irrational. From this, you can see that the negation is that there exists a rational number R and an irrational number S, such that R plus S is rational. It follows that the starting point and what is to be shown are as follows. Suppose not. Suppose there is a rational number R and an irrational number S, such that R plus S is irrational, or is rational. Show that this supposition leads to a contradiction. To derive a contradiction, you need to understand what you are supposing. That there are numbers R and S such that R is rational and S is irrational, and R plus S is irrational, or is rational. By definition of rational and irrational, this means that there are convenient expressions that can be substituted for R and R plus S. But all you can say about S is that it cannot be written as a quotient of integers. If you substitute 471 into 472, you obtain A over B plus S equals C over D. Subtracting A over B from both sides gives you C over D minus A over B. Rewriting C over D and A over B as equivalent fractions, and by the rule of subtracting fractions with the same denominator, you get BC minus AD over BD. Now both BC and AD minus AD and BD are integers because products and differences of integers are integers, and BD are not equal to 0 by the product property. Hence, S can be expressed as a quotient of two integers with a non-zero denominator. And so S is rational, which contradicts the supposition that it is irrational. So the sum of any rational number and any irrational number is irrational. Argument by contraposition. A second form of indirect argument by contraposition, is based on the logical equivalence between a statement and its contrapositive. To prove a statement by contraposition, you take the contrapositive of the statement and prove the contrapositive by direct proof, and conclude that the original statement is true. So, you express the statement to be proved in the form of for all x in D, if P of x, then Q of x. Rewrite the statement in the contrapositive form. If Q of x is false, then P of x is false. Then prove the contrapositive by direct proof. So you show that you suppose x is a element of D such that Q of x is false, and then show that P of x is false. These slides don't always show up very good. Prove that for every integer n, if n squared is even, then n is even. First, form the contrapositive of the statement to be proved. For every integer n, if n is not even, then n squared is not even. By the quotient remainder theorem with divisor equal to 2, any integer is either even or odd. And by theorem 472, no integer is both even and odd. So if an integer is not even, then it is odd. Thus, the contrapositive can be restated as follows. For every integer n, if n is odd, then n squared is odd. So proposition. For every integer n, if n squared is even, then n is even. Relation between proof by contradiction and proof by contraposition. Observe that any proof by contraposition can be recast in the language of proof by contradiction. In a proof by contraposition, the statement, for all x in D, if P then Q, is proved by giving the direct proof of the equivalent statement, for all x in D, if not Q, then not P. To do this, you suppose you are given an arbitrary element of D such that Q of x is not true. Then show that not P of x is true, or show that P of x is false. So to rewrite the proof as a proof by contradiction, you suppose that there is an x in D such that P of x is true and Q of x is not true. Then you follow the steps of the proof by contraposition to deduce the statement, not P of x. But P of x is a contradiction to the supposition that P of x is true and not Q of x is true. Because to contradict a conjunction of two statements, it is only necessary to contradict one of them. So, you can do this for every integer n. If n squared is even, then n is even. Proof as a problem-solving tool. Direct proof, disproof by counterexample, and proof by contradiction and proof by contraposition are all tools that may be used to help determine whether statements are true or false. Working with examples might have given you a sense that a statement of the form, for all elements in a domain, if the hypothesis is true, then the conclusion is true, might be true. To explore further, imagine elements in the domain that satisfy the hypothesis. Ask yourself, must they satisfy the conclusion? If you can see that the answer is yes in all cases, then the statement is true and your insight will form the basis for a direct proof. If after some thought it is not clear that the answer is yes, ask yourself whether there are elements of the domain that satisfy the hypothesis but not the conclusion. If you are successful in finding some, then the statement is false and you have a counterexample. On the other hand, if you are not successful in finding such elements, perhaps none exist. Perhaps you can show that assuming the existence of elements in the domain that satisfy the hypothesis and not the conclusion leads logically to a contradiction. If so, then the given statement is true and you have a basis for a proof by contradiction. Alternatively, you can imagine elements of the domain for which the conclusion is false and ask whether such elements also fail to satisfy the hypothesis. If the answer in all cases is yes, then you have the basis for a proof by contraposition. And that will bring us to the close of today's lecture. Remember, we're going to finish up Chapter 4 on Tuesday, and then have your midterm on Thursday. Grades will be posted on Canvas and Pause before the close of business the following Monday. Have a good day. See you on Tuesday. Have a good weekend.